start. So, we left off last time talking about energy. And what we need to really do is talk about how it is energy is used and converted within biological systems. So you'll remember that we talked about two laws of thermodynamics. The first of which said, basically, energy can either be created nor can it be destroyed. And really, you can look at our universe as a closed system, right? There's a finite amount of energy available to us, and that's all that there's ever going to be. However, energy can be converted from one form to another, and that's what plants do through the process of photosynthesis. They're able to take solar radiant energy and convert it into a chemical type of energy. And that's what we do as well. We're able to take the plant's chemical energy and convert it into another form of usable energy for ourselves. Conversion, however, is not perfect. There is a second law of thermodynamics that suggests that all levels of organized energy, and when we talk about organized energy, really what we're talking about is biologically important molecules, right? And those molecules represent some amount of energy, and that energy is a product of chemical bonds between them. And so what the second law suggests is those levels or degrees of organization of energy are all tending towards disorganization. That's called entropy. It's the natural process whereby things become disorganized and unstable. So when we convert energy from one form to another, really what we're doing is performing chemical reactions. So for example, plants are able to take solar energy and they're able to create a molecule called ATP and another molecule called NADPH that we'll talk a lot about next week. And with these two molecules, they're able to drive a series of chemical reactions that takes a carbon dioxide molecule and makes it huge, makes it 6 carbon atoms stuck to 12 hydrogen atoms stuck to 6 oxygen atoms. Okay, and that's, again, a chemical reaction. So before we start talking about chemical reactions and how we affect the rate of chemical reactions, we need to define a couple of terms. The first of which is a reactant. So a reactant is some molecule or substrate or atom that we're using to make into something else. So in the context of photosynthesis, we're taking carbon dioxide and water as our reactants. And then the products of that are going to be oxygen gas and sugar. So we refer to reactants in the context of chemistry as substrates. So a substrate is something on which typically a protein enzyme is acting. And the products, again, are whatever we produce from that chemical reaction. So in the context of photosynthesis, it's oxygen gas and sugar. Now, reactions occur really in two forms, and we've talked about these two different types of reactions before. There's something called an endergonic and something called an exergonic reaction. And really we define that as the relative amount of energy represented by both products and reactants. So an endergonic reaction is one in which we invest a bunch of energy so that the products represent a higher state of complexity or energy than the reactants originally did. And I've diagrammed that here, or rather your textbook diagrammed that here. So along this this y-axis, this shows you relative energy state. And the higher up on the y-axis you go, the higher the energy state. And the x-axis represents the time elapsed within a chemical reaction. And so what this is suggesting is that the original reactants had some neutral kind of energy state. And as that reaction progressed, the relative energy state of those products increased when compared to the reactants. That's endergonic. That's something into which we are investing some energy. And really the best way to think about it is to take something that is simple and make something that is complex. So if I was, I'll write the reaction that is photosynthesis. In photosynthesis, what happens is we take some H2O and some carbon dioxide. We're going to take 6 of these and 6 of those, and we're going to convert that into C6H12O6 plus 6 oxygen molecules. So can you see that the reactants here look much simpler than this molecule here? We've increased the complexity of those products. And when we increase complexity, that is inherently an endergonic reaction because we have to invest energy into that process. Another really good example of an endergonic reaction is the anabolism of muscle. So when we're building muscle, we're creating more muscle fibers, right? To create more muscle fibers, we have to invest energy so that that muscle complex becomes a little bit larger. Alternatively, reactions can be exergonic. And an exergonic reaction is one in which energy is released. So we take a complex molecule, we break some bonds, and then energy between adjacent atoms is released. So the catabolic process of breaking down a muscle is another good example of that. Or cellular respiration, which is the process or the chemical reaction that we use to take sugar and to digest it. So with cellular respiration that we'll talk about in a couple of weeks, what we do is we take a sugar molecule, C6H12O6, and we add to it 6 oxygen molecules. And then from that reaction, we end up with 6 water molecules and 6 carbon dioxide molecules, plus a whole bunch of ATPs. What's the relationship, you guys, between photosynthesis and cellular respiration? They're opposites, right? They're mirror images of each other. What are the reactants or the substrates in this reaction are the products in this one. And then the reactants of this are the products of that, right? And then the products of this become the reactants of that. There's this beautiful symmetry in nature where the things that we're using to break down, other organisms are using to make the stuff that we break down, and vice versa. Okay, so does the difference between an exergonic and an endergonic reaction make sense? Again, if we look at this diagram, what we see with an exergonic reaction is the substrates, or the reactants, have this intermediate energy level, right? Then over the course of this chemical reaction, we have products that have a lower energy state than the original reactants do. Some energy was released, consequently it's exergonic. Now you'll remember that in laboratory when we looked at that with the liver's enzymes, exergonic reactions produce or release energy, and some of that energy is released as heat. And so if you hold on to an exergonic reaction, you can actually feel the heat in your hand. Okay. So there is a natural barrier to entropy. And that natural barrier to entropy is the energy of activation. I mentioned before that covalent bonds are incredibly stable. And what stability in molecules means is they don't fall apart randomly very often. They'll stay together pretty well. Like a water molecule, it's a fairly complex molecule. You have 3 atoms that are stuck together and they're sharing electrons. Water molecules don't often just randomly fall apart, even though entropy is suggesting that they should. And the barrier to that is this idea of activation energy. And activation energy is the amount of energy required to cause a chemical reaction to occur. So we could take a sugar molecule, for example, and we could drop it into some water. And we could wait for some amount of time, and eventually that sugar molecule would just randomly fall apart. those bonds would become unstable, and adjacent carbon atoms would just disassociate from each other. When that happened, the energy represented by those covalent bonds would be released into the water. But that process takes an incredibly long time. And really that's what we're doing with metabolism, right? When we consume some food, what we're trying to do is extract the energy in those chemical bonds from that food. And our bodies can't wait for entropy to cause these molecules to fall apart and to release that energy. What we have to do is we have to make this energy of activation a little bit smaller. That is, we have to figure out some way to make chemical reactions occur a little bit more easily. So what happens is a process called catalysis. And catalysis is adjusting the rate of a chemical reaction. Generally, what happens is we're increasing the rate of chemical reactions. And the way that we do that is by decreasing the energy of activation. So let's think about this for just a minute. I'm going to draw a reaction on the board, and you guys are going to tell me whether it's endergonic or exergonic. Endergonic or exergonic reaction?
Exergonic.
Exergonic, right? Because the products have a lower energy state than the reactants did. So the area, or the activation energy, is defined as the distance between this point and this point. So that's the energy of activation, or the E sub A. Now this is what cellular respiration looks like. It's an exergonic reaction. We start off with a complex molecule of sugar plus some oxygen, and then we're going to break it down into carbon dioxide and give off a little bit of water as well. And so nature also does this. And so what nature does is it invests a whole bunch of energy into that sugar, and then all of a sudden we reach some point of destabilization, and then that reaction just occurs spontaneously after that. But there is required this rather huge energy investment, okay? So what we can do with some molecules called enzymes is we can catalyze that reaction or lower the energy of activation that's required. So that with enzymatic activity, that energy of activation is greatly reduced. Now, the same thing has happened, right? We've still accomplished the same amount of energy release because this energy up here doesn't count. And why doesn't that energy released up above the energy state of the products, or excuse me, of the reactants count? Why is this unimportant energy right here, do you think? Yeah, Carly.
Because it hasn't gone past that point of energy of activation.
I love it. So what we've had to do here is we've had to invest energy, right? And so we're actually spending some energy to right here. And then we're reclaiming the energy that we already spent. So right at this point, there's a net zero gain. It's really the difference between this point and this point that is energy increase for us. Does that make sense? Think about it in terms of investing your money, right? So let's say we want to purchase some stocks. We have to invest some money into stocks, and then we have to wait for some time for those stocks to increase in value to equal the amount of money that we've already invested into those stocks. Then once we've surpassed the amount of money that we've invested into it, everything else goes straight into our pocket as a gain. Does that make sense? You could also think about it in the context of home equity, right? Okay, so energy of activation really represents negligible energy. We have to invest in order for something to occur. So, the real value of enzymes in biological systems is decreasing that amount of investment. That's insider information, right? We know the best time to invest, or we reduce the amount that we actually have to invest in order to get some amount of energy. So what exactly is an enzyme? We talked about enzymes a little bit already, and you'll recall that an enzyme is not but a protein. And by far the most important aspect of any protein is what? Its shape, yeah. Its shape is going to affect its biological activity. So there are enzymes that catalyze a reaction by decreasing the amount of activation energy. Many of our enzymes do exactly this. But there are some times when we're actually going to want to inhibit reactions as well. And so there are other enzymes that might increase the energy of activation so that chemical reactions are less likely to occur. Can you think of a time when you wouldn't want a chemical reaction to be occurring? Let's talk about cellular respiration specifically. Can you think of a time when you aren't actively wanting to generate a whole bunch of energy?
When you're sleeping?
When you're sleeping, exactly right. So there are definitely times in our lives when we want chemical reactions to be occurring, and then there are other times when we don't want those chemical reactions occurring. And enzymes are one of our main regulatory structures. So the shape of the enzyme is really going to determine how it functions in a biological system. And there are a whole bunch of factors that influence the shape of proteins that we'll talk about in just a couple of minutes.